coherent. I can't do too many things simultaneously early in the morning. Come on, error handling. Here we go, we had that. So we construct this automaton. We began talking about the non-deterministic version. Each state of the automaton is labeled with an LR0 item. Okay? And going a little bit further back even, what an LR0 item says, the stuff to the left of the dot says that's what the parser has seen already. The input has something that is derivable from this part to the left, and therefore the stuff to the right is one possible continuation. The reason we say one possible continuation is that obviously we haven't actually looked at the rest of the input, so we don't know how it actually continues. But if the parser is in this state, that's a possible continuation. So it might see a 1, and if it sees a 1, it would go to this state, and then whatever happens. So we have transitions on epsilon, which makes it a non-deterministic automaton. We have transitions on non-terminals, and we have transitions on tokens. Now, what we'll do with this non-deterministic automaton is convert this to a deterministic automaton. That construction is pretty much straight out of standard techniques for converting non-deterministic to deterministic automaton. What is this automaton good for? What this automaton tells us is each state is labeled by an item in the non-deterministic case. When we go to the deterministic case, like I said, it's a standard non-deterministic to deterministic conversion. In the deterministic case, each state of the deterministic automaton will have a set of these items. If you remember your y.output file, each state has a set of items. Okay, so that's where that comes from. Each state then says that if the parser lands in this state, here's how it could have gotten here. For example, in this state here, the parser got here because other stuff happened, but most recently, it started processing a production for S, and it saw a 0, and that's how it's in this state. So that's the sort of information each state will have. Okay? And then we'll look at the transitions out of the state, and if I see a token, for example, I'll say, okay, we'll shift that token to move from this state to that state, because if I see that on the input, I can declare, yes, I have seen that token, so now I can move to a state where I have seen that token, and I'm looking for the rest. So that's the essential idea. So here, let me quickly talk about the construction of a deterministic automaton from a non-deterministic automaton. If you already have seen what's called the subset construction, which is an algorithm that converts a non-deterministic finite state machine to a deterministic finite state machine, this is exactly what that is. If you haven't seen it, then this is what it is. First, I'm going to talk about so I'm going to have two sets of functions. One set of functions will say, starting from a given state, set of items, if I take just epsilon transitions, what set of items can I get to? Okay? In the subset construction, that's called an epsilon closure. And then I'll say, given a deterministic automaton state, which has a set of items, for any given symbol, like the symbol 0 or the symbol S, for any given symbol, what set of items can I get to? Okay, and we'll keep repeating this process. So I have a set of LR0 items. Okay, a set of LR0 items. Again, each of these guys, each of these dotted thingies is an LR0 item. And so when I go from the non-deterministic guy to the deterministic guy, what happens to each state in the deterministic automaton? It's a set of items. That's what I'm talking about over here. Okay, if I have a set of LR0 items, how do I work with that set? Here's the notion of a closure on that set of items. This is the analog of epsilon closure in subset construction. Everything that's in the set of items I is added to closure of I. Okay? So I start with a set of LR0 items, and I'm going to close it off looking only at epsilon transitions. everything that's in I, I'm going to add to closure of I. So that's the first step. Then I'm going to look at every item of the sort A goes to alpha dot B beta, where this is a non-terminal. Okay? And I'm going to take every production B goes to gamma, and I'm going to say, I'm going to add the item B goes to dot gamma into the closure of I. Now, so what this does is it looks at items that are already in the closure, and I've initialized my closure now, right? So I look at things that are in the closure. I look at everything that has a non-terminal to the right of the dot. I look at every production for B, and I add the item B goes to dot gamma. And I keep doing this. Until no new items can be added. Actually, this could be moved out of the repeat loop, I guess. Okay, so I keep doing that until no new items can be added. So what's the intuition? What the intuition is that if this item is in this set, that means in that state, because each set of items corresponds to a state, in that state, the parser has seen something that alpha could derive. And it's looking at potentially something that B beta could derive. Okay? So if it's potentially looking for something that B beta can derive, in order to see that, it has to first see something that B can derive. So in order to see something that could be derived from that, it must be the case that it first sees something that can be derived from B. Okay? Well, if I see something that potentially could be derived from B, how could I do that? I have to use one of the productions for B. So I have to use some production for B. And since this is to the right of the dot, I haven't seen any of that yet. So I look at the production for B, and I say, for each production for B, I can see the right-hand side for that production as something that could come next. So I put the dot all the way on the left. Okay? So that's the intuition. All right? If A goes to alpha dot B beta is in closure, that means that something that's derivable from B beta is legal at this point. And this means that something that is derivable from B, and thus from gamma, which is the right-hand side of a rule for B, that's legal at this point. Okay? So I keep doing this until I can't add anything new to the closure set. Sometimes, some people find it easier to think of sets and set operations. Some people find it easier to look at transition diagrams and think of what's going on. So let me go and restate that closure in terms of these transitions. Let's see. Did I have any more? No. So I have these transitions, and this transition, says that if I'm in a state, A goes to alpha dot X beta, X is a non-terminal, then I have an epsilon transition to a state where I have the item X goes to dot gamma. X goes to gamma as a production. Right? This was how I constructed my non-deterministic automaton. And what that closure set computation was doing was collecting all of these things that make epsilon transitions. It was collecting them up into a set. So that's just closing off everything under epsilon transitions. Okay? If you are accustomed to non-deterministic automata, then this seems like a natural thing to do. If you aren't accustomed to non-deterministic automata, if you haven't seen them before, this is exceedingly weird, because this machine is kind of going and acting on its own. And non-deterministic automata initially can be very counterintuitive. What the closing off under epsilon computations is doing, this computation here, it's saying that once, beginning with some set of items, which is some DFA state, beginning with that set of items, what I'm going to do is I'm going to compute all of the states that I can reach, all of the items I can get to, without actually consuming something from the input. So those are just the transitions that I can make on epsilon. Okay? Questions?
Do you explore all transitions in a finite section? Like, in this example, like if there was like 5 different epsilons to go to
The question is, if I have 5 different epsilons out of a state, will I look at all of them? So in short, do I explore all transitions? Yes, I would. So if you look over here, I say if A goes to alpha dot B beta is in the closure of I, and B is a non-terminal, then for each production of B, I throw in B goes to dot gamma. Okay, so if B has 20 productions, I'm going to throw in 20 of these B goes to dot something into the set. In the non-deterministic automaton, that would correspond to 20 different epsilon transitions out of that state on B. Okay? Other questions? The other, so this closure tells us how we kind of let this automaton explore out all the epsilon transitions and gives us the set of states we can get to using only epsilon transitions. Now we get to really make transitions on non-epsilon symbols. So here's the deal. If I have a set of LR0 items I, and I say, okay, here's the set of items. So whenever I say set of items, think DFA state. Okay, the two are the same thing. Because really, what we'll be contending with are DFA states, and each DFA state is a set of items. Here I have a DFA state, and I have some grammar symbol x. Okay, so x could be a variable, it could be a token. So I have some grammar symbol. Question, if the parser is in this state, in the state given by the set of items I, and we say, okay, this parser in this state now actually sees this grammar symbol, what state does it transition to? I'm using C's kind of liberally here. If x is a token, it makes sense to talk about the parser seeing the token in the input. If x is a variable or a non-terminal, same thing, right? If x is a non-terminal, then what does it mean to see that non-terminal? What it means is that the parser has found some sequence of tokens that could have been derived from x. Okay? So now it says, okay, I have seen something that x could derive, so I have seen x. I've seen an expression. I have seen a function. I've seen a statement. So it's in this state I, it sees x. What does it go to? What state is the next state? The computations, it's easy enough to write down, but it takes a little while to think about it and kind of internalize it. So here's the deal. Here's my state. Okay, here's the state that I began in. That state has a whole bunch of items like this. Okay, so it has a whole bunch of items like this. And what that is saying is that in this state, the parser has seen something that alpha could derive, and here are all the, all sorts of different possible continuations that are legal at this point. Since the parser doesn't actually know what's coming down the road, it can't say one of these is the right continuation. It simply says, if I'm in this state, I could go this way, I could go this way, I could go this way. Here are the possibilities. Some of those possibilities will have x to the right of the dot. The intuition being that some of those possibilities will expect something x can derive next, and others might have other things to the right of the dot. I've told you that we've just seen x in the input. So really all I care about are the items that have an x to the right of the dot. Okay? So suppose the parser is in a state, and it has two items. A goes to alpha dot x beta, and the other one is A goes to y, alpha dot y gamma or something. So one of them says, in this state, I could see something that x can derive and some other stuff. The other one says, in this state, I can see something that the continuation could be something that y could derive and some other stuff. So now we find out that, in fact, we've seen x. Well, the future corresponding to the y item is irrelevant at this point, because I've just discovered that I know what the outcome is. So I pick out the ones that correspond to what I've really seen. Those are the ones that have an x to the right of the dot. Since I've seen x, that's what I'm told, right? I'm told you've now seen x. Since I've seen x, I can actually walk the dot across. In the new state that I get to, I have now seen alpha x. What am I waiting for? I'm waiting for beta. So I walk the dot across. And at this point, I say, OK, now that I've moved to this new item, let's find all of the states that I can reach via only epsilon transitions. So I close off on under epsilon transitions. That's the closure. OK, so that's what's going on. The actual implementation is relatively straightforward, right? To compute, go to from I on X, I pick up all the items in I where this guy appears to the right of the dot. That's these guys. Walk the dot across the X, and I compute the closure. OK? Here's an example. It's much too early in the morning to have all this abstract stuff without an example. So here's my initial item, I0. So S prime goes to dot S. Do you remember where S prime came from? We added this symbol. It's a new start symbol which does not appear elsewhere. And we added this production. And the idea was that this way, this ends up simplifying some aspects of the parser, because S can be recursive. And in fact, we do have some grammar rules where S appears on both on the left and the right. But S prime doesn't show up elsewhere, and that makes it easy to recognize when I should stop. So here's the very initial item. S prime goes to dot S. And what this says is that at the very beginning, when the parser starts out, I haven't seen any of the input, but I'm looking to see something that the start symbol could derive. So that's what I say at the very beginning, right? So that's the NFA that we saw before. So let's talk about closure from this initial state, which is this NFA state over here. In the NFA state, if we look at the NFA state from here, where could we go to on epsilon transitions only? We can get from here to here and here to here, and that's basically it, right? So if I compute a closure on I0, I'll have this, and this. Closure of I0. S prime goes to dot S. There's a non-terminal to the right of the dot, so I pick up each production for this guy and put a dot on the left. Here's my production for S. Here's the other production for S. Oh yeah, minor detail. If I have an epsilon, then it doesn't make sense to talk about a dot to the right or the left of the epsilon, because an epsilon means there's nothing there. It's the empty sequence. So you just put the dot on the right-hand side. So that's my closure of I0. And pictorially, that's starting here, all the states I can get to traversing only epsilons. So here's my set of items. Now, go to from I1 on the symbol 0. So I1 is the closure of I0, which is this, and this, right? So we ask, OK, from this set, what states can I get to on the token 0? Well, I have a transition on 0 from here. I can get to this guy. And since I have a transition on 0, I can get from here to here and then take an epsilon transition. And I can get from here to here and take this epsilon transition. Well, in this case, they don't add anything new, right? Because if I go from here to here, and then epsilon transition gets me back to something that I had already. This epsilon transition gets me back to something I had already. So here's the set computation. Okay, I'm showing you both because I want you to get your intuitions, both in terms of what I'm computing. Sometimes if the grammar is large, drawing a picture becomes unwieldy. But also, looking at the picture makes it easier to ground your intuitions about what this computation is doing. Yeah?
So we're basically just figuring out the whole transition function of the NFA.
So we're basically, what we are doing is we're figuring out the transition function for the DFA. Okay? So go to from I1 on 0. Here's I1. I1 is S prime goes to dot S, S goes to dot 0 S1, S goes to dot. Go to I1 on 0. So think about this parser state. Okay, this is a state in the parser. And this looks at the various possibilities that the parser sees in terms of parsing the input. And then we say, okay, you're in this state and you see a 0. What happens? Well, this is the only relevant item here. So I pick that up. I've seen a 0. Go to from I1 on 0 says, you've seen a 0. What state do you go to? Since I've seen a 0, I walk the dot across. So that's what I get when I walk the dot across. This is the only item in this state that has this symbol to the right of the dot. Okay, so I take my state and I pick up all of the items that have this guy to the right of the dot. Well, there's only one over here. Walk the dot across, compute the closure. Computing the closure corresponds to taking this and that epsilon transition. When I compute the closure, look, there's a non-terminal to the right of the dot. So I throw in all of the productions for this non-terminal with the dot all the way on the left. And that's this guy and this guy. And that's my new state. Now I have a new state. That's the goto of I1 and 0. And I can compute gotos out of this state as well. So for example, this from this set of items, if I wanted to compute goto on the symbol S, what would I get? Sorry?
I think you'd be done, right? Because you were looking for an S, and now you found one, so you're done.
Well, I want to compute the goto from this state on this symbol. On the symbol S. That's going to be a state. Sorry, a set of items. What's that set of items?
In other words, you were at L1.
I am in this set of items.
You are at that point right now.
Right, and I want to compute a goto on S from this set of items. So you pick up all the items that have S to the right of the dot. How many are there? 1. Walk the dot across. What do you get? 0 S dot 1. Compute the closure. What do you get? 0 S dot 1. Why is that? Why does it not change? Because it's a token. Because in that, so once I walk the dot across, this is the only item I have. The dot's over here. So S goes to, let me write it out. I pick up, S goes to 0 dot S1 and the others. This is the only item in this set where the symbol I'm interested in appears to the right of the dot. And I say, okay, in this state, let's suppose I've seen something that S can derive. What's the next state? Well, I pick this item up, I walk the dot across. So now I have this, and I compute closure of that set. Well, what the closure does is if there are any non-terminals to the right of the dot, it throws in additional productions for those non-terminals. This is a terminal. So nothing new gets added. Okay. Again, it's really important to to kind of anchor our intuitions as to what's going on. I mean, I see sometimes, it's really easy to fall victim to this, where someone carries out a computation, runs an algorithm, without us having a sense of what does the result tell me about what's going on in the computation. So let's see what the result of that particular goto computation told us. So this is equal to this same set, 0 S dot 1. And that was equal to goto of this state over here. S goes to 0 dot S1, etc. on the symbol S. Right? So intuition time. I'm in this state. So the parser is in a state where it's just seen a 0, and maybe one possible continuation is to see something that S can derive. Or maybe it's seen some other stuff and we haven't kept track of it, but one possible continuation would be to see a 0. Or maybe it's seen some other stuff, and I'm not sure what that means. We'll come back to that later. Okay? But this corresponds to the S goes to epsilon. And now I say, okay, in this state, I tell you, parser, that you have now seen something that S could derive. Okay, so if I've seen something that S could derive, at that point I say, okay, this grammar, so now I'm going to back up a little bit. This grammar is the grammar of a whole bunch of zeros and an equal number of ones, right? 0 to the n, 1 to the n. So I've seen a 0, then I see something that S can derive, and inductively S derives some number of zeros and an equal number of ones. So at that point, what the parser needs to do is to say, okay, since I have now recursively seen something that S can derive, what I need to do is check that I have a 1 in the input to balance out my 0, and then I'm done. That's what this state is doing. It's saying that, okay, I was in this state, 0.S1, I saw something that S could derive. So now in the new state, I have seen something that 0 and S can derive, and I need to see a 1 to balance out that 0 that I had previously. All right? Questions? Okay, so now I'm going to use those two functions. We talked about there's a closure function, there's a goto function. And I'll use those two functions to construct the set of parser states. Just stepping back for a second, to situate ourselves. We started talking about bottom-up parsing many lectures ago. And it was all nice and kind of magic-y, because if we were given this magic parse table, things worked great. And the parse table told us, now you should shift, now you should reduce, now you should do whatever, now you should work on Brian's resume. No, the parse table won't tell you that. So the parse table was this magic thing that contained all the knowledge about the parsing. The parser itself was this really, really straightforward computation that says, look at the next token, look at the state, consult the parse table, it'll tell me what I need to do. So all of the action was in constructing the parse table. Now that's what we're talking about. How do we construct the parse table? Okay. Let's take a really quick 2-minute break, and then I want to come back and talk about how we construct the parse table.